Hi everybody, today we're going to be talking about primes with me. The goal being we want to prove that if P divides the product of primes, then P is going to be equal to one of those primes that's being multiplied together. So for instance, intuition-wise, I know 3 does not divide whatever number this multiplies out to be. And I know that because these are all prime numbers, and none of them are 3. 3 doesn't divide 5, 3 doesn't divide 23, 3 doesn't divide 61, because they're all prime. Okay, but before we jump off into a deep end, let's take a moment and formally define prime, even though I'm sure you guys all know what it is. So we call a number prime if it is greater than 1 and its only positive factors are going to be 1 and itself. Otherwise, we call the number composite. All right, so I'm pretty sure we were all on that page, but now we for sure all are. Let's start with a simple exercise. We are going to prove that if we've got a number that is greater than 2 and that number is prime, then it's going to be odd, aka 2 is the only even prime number. We all know that, but let's take a moment and let's prove that. It's pretty easy if we go about it via contradiction. So here we go. We're going to suppose that there is a prime number P, and it is greater than 2, and it is also even. We know what it means to be even. We know that we can say that P then equals 2 times K, where K is specifically an integer that is bigger than 1, because P is bigger than 2. So that means that 2 and K are going to be factors of P. Then 2 and K are 2 positive factors of P, and they are not P or 1. This directly contradicts the fact that P is prime. So then we can conclude P is not even. Okay, so nothing overly heady, just to get us warmed up. Now we're going to move into a lemma that is a little bit more heady, but super, super useful. If we have a prime number P and it is dividing the product of n many integers, then P must divide explicitly one of those integers. We only get this because P is prime. Because let's say we're talking about 4 times 5. I could say that 2 divides 4 times 5, but I also only get that because 4 divided 2 explicit, or 2 divided 4 explicitly. However, I could also say that 10 divides 4 times 5. However, 10 does not divide 4, and neither does it divide 5. So again, we only get this because P is prime. So let's go ahead and try and prove this. So what I'm going to say is that since we're working with something that looks vaguely n-ish, because I is going 2, 3, 4. By the way, it starts at 2 because otherwise you say P divides A1, then P divides A1, and that's horrendously boring. Well, completely true, horrendously boring. So it starts at 2, which means we're working with something kind of natural numbersy. I think this is going to be a proof by induction. So, by induction, My base case is the smallest possible I that we have, which was 2. So n equals 2. So we assume that P is going to divide A1, A2, and we're going to work towards concluding that P divides either A1 or A2. It divides at least one of them. I see this and I'm like, well, either it divides A1 or it doesn't, which that turns into cases. So we're going to prove the base case by cases. This is definitely like nested proof stuff right now. Case 1, P divides A1. If P divides A1, then we've gotten it. We have gotten the fact that P divides one of those integers. So we're done. Things get more interesting in case 2, where I say that P doesn't divide A1. Now we have to be like, okay, well, if it didn't divide that one, it's got to divide the other one. So that's where we're headed. Okay. What can we do about this? So if P doesn't divide A1, then what we get to say is the GCD of P in A1 is going to be what? It's going to be 1 because P is prime. So then, now that we have the GCD, we have a very handy lemma from the very end of our last lecture called Béziers' theorem, where we can say there exists an S and a T such that S times P plus A1 times T is going to be equal to 1. So then what we're working up to is we want to be able to talk about, we want to be able to make use of the fact that we had an A1 times A2. And so I'm going to suggest we multiply by A1 or by A2. That way we can get an A1 times A2 sitting in here. So SP times A2 plus A1 A2 T is equal to A2. How is this helpful? Well, remember the goal is we want to be able to divide by A2, or we want to divide A2 because we couldn't divide A1. So what can we say about this side in terms of dividing by P? P divides this guy because P is sitting right there. And then P divides this guy by assumption. So that means that the left-hand side of our equation is divisible by P. So then P divides SP, or we'll write it out a little bit more. Since P divides SPA2 and P divides A1, A2, T, P divides SPA2 plus A1, A2, shift all of this, times T. And if it divides that, remember that's equal to A2, so then P divides A2, and that is exactly where we wanted to go. So then we can back out of the like by cases part, I guess, sort of, make the indents match. There we go. And conclude that P divides A1 or P divides A2. There we go. That's the base case. Now it's time for the inductive step. Okay, so we're going to assume that if P divides n many integers, implies that P divides one of them specifically. So now what we start with is we assume P divides any combination of n plus 1 integers, and we want to get down to P divides one of those integers. So what we're going to do is we're going to use the base case first this time. I'm going to say, like, this is an integer. This is an integer. So I have two integers multiplied against each other. So then P divides A1 to AN, so our group of n, many integers, or P divides the n plus 1, 1. And that's from the base case that we just did. But now what we have is we have P is dividing a group of n many integers. That's what we originally assumed, is when we divide any group of n many, then we're left with being able to conclude that it divides at least one of them. So now we apply our inductive step. So then P divides AJ, where J is one of these guys. Or P divides AN plus 1. By the inductive assumption. That was a terrible M. There we go. So now, that's basically all I wanted. But now we can write it out as, so P divides anything 1 to n or n plus 1. So we can just add that onto our indices right here. So P divides AJ for j going 1 to n or n plus 1. So now we have proved the inductive step. We're done with the inductive step, which means that in general, the entire theorem holds. Okay. Now that we've proved that, what we really wanted to prove today actually follows pretty quickly. What we wanted to prove today was that if P divides some prime numbers Q, then P is going to be equal to one of those Q's. Basically, the logic follows if P divides one of those numbers, which we get from the lemma we've just proved, then P is going to have to be equal to one of those numbers because it was prime. And so the only factors are 1 and itself. And I'm going to leave that for you guys to do. And I advise you do it because it's going to be the first problem on your worksheet. All right, that's all I've got for right now. This sets us up for a really good place for our next lecture, which is going to be like the big result for prime numbers in this chapter. So I'll see you guys all next time. Bye.